And welcome. How are you all doing?
Pretty good.
All good, all good. How do you feel about SuperCollider? Yeah, getting there.
Yeah.
How do you feel about me? Even worse, yeah? Cool, so we'll continue along the lines of what we've started. So we've done a bit about modulation. Yeah, you're all clear with amplitude modulation, ring modulation. FM, did we do a bit of that? Or did we just stopped short of FM? Yeah, I'm a bit confused because I'm running the same class for Hungarian guys. Or let me say Hungarian speaking, because I'm only merely Hungarian speaking. So we're going to briefly look at FM to wrap up the modulation type stuff. And then I hope we get to, well, we'll see how far we get. So what is the product of audio rate modulation? It is the one crucial term that I have repeated many times, and I want you to be very sure about it. It is some frequencies and different frequencies, we call them sidebands. Okay, so try to now I'm thinking Hungarian. Make it your own. Okay. Cool, so sidebands, as I just announced, some frequencies and different frequencies. Now, the interesting thing to note is that we have pretty much the same thing with FM, right? The difference will be that the frequency modulation will give us further sidebands, in other words, higher order sidebands, okay? So this term, first order, second order, third order, have you encountered this before, maybe? In the context? Typically, I mean, if you, at least when I was a kid, the first encounter was through crossover networks for speakers, where you would have different filters, and typically a 6 dB slope filter, 6 decibel per octave, to be accurate, is a first order filter. Second order is 12, third order is 18, and so forth. So it's a kind of order of processing. Essentially, it signifies layers of processing, typically as well. We'll talk about filters later. So what we have then is that the first order sidebands are the sum and the frequency and the difference frequencies. The second order will be twice the first frequency plus the second, twice the first minus the second, and first frequency plus twice the second and first frequency minus twice the second. So we're actually essentially integer multiplying the frequencies and continuing to take all the combinations in terms of sum and difference frequencies. So the way this will look like, obviously I'll show you as well, but as you remember what we had from a single frequency, right? As we increased the modulation frequency, we were departing in both directions. And in certain cases, the original was left behind. In certain cases, it wasn't, right? So that was AM and RM. And now what we will get is that we will get a range of frequencies spreading out. So not just a single pair of sidebands, but multiple sidebands spreading out. Okay? So, first basic thing to understand probably is how we draw something along these lines. So typically we operate with sine oscillators, and in this case what we will have is, unlike in the previous cases where we had a multiplier which combined the two outputs, now the output of a single oscillator will essentially control the frequency of the other oscillator. So you've probably seen this already. In fact, if you have used some kind of FM synth, maybe FM8 or something along these lines, then typically what you would get is a graph that looks like 2 going to 1, or 1 going to 2, or 3, one above the other, and so forth. And essentially that will all amount to the top oscillator controlling the frequency of the bottom oscillator. Okay? So, what do I need to make this a complete graph? What are the parameters? So first of all, I specify that I'm controlling the frequency of the bottom oscillator. The other thing that might be useful is to specify the QR, great, to specify the modulation frequency. Let's do 5 Hertz, okay? And then what's left? The range. Yeah, you see, because what is the original range of an oscillator typically? As usual, we've said it about 10 times in the last 3 sessions. -1 to +1. So if I send values -1 to +1 to the second oscillator, it will produce inaudible frequencies between -1 Hertz and +1 Hertz. So that's not sufficient. I will need to specify a range. And in this case, I will use this convenient way of doing it. Oops, how did I make that bold suddenly? So I just put it here on the side, and the top is the maximum value, bottom is the minimum value. Okay? Cool, so this is your basic FM. Anything missing? Well, I could be as pedantic to make another arrow towards the kind of output, whatever, but that's fine. Okay, so warm up, please code this. Okay, I will run to the toilet and be right back. Cool, so fairly straightforward patch. So what we need to do is, instead of this number, which is a fixed frequency at this stage, what we need is another oscillator. And what we had there is, oops, sine oscillator, audio rate 5 Hertz, and the range between 100 and 500. Okay. That's the one. Cool. All right. Now, what is the spectrum of this? Oops, freak scope. So you see what's happening is that I have an oscillator, a sine oscillator, moving up and down in frequency. Yeah? So what happens if I increase the modulator frequency to 15? So now you see that it's not moving regularly. Why not? A minute ago you could see it moving regularly, and now it's a bit jittery. There's something funny about it. Why would that be? Well, it has to do with the fact that I am nearing the screen refresh rate. So it's a bit of an anomaly, really. But I think it's worthwhile asking these questions because, rather than assuming, if you want to learn programming and also critical thinking, you always have to think about everything, right? So avoid being satisfied with something. Oh, well, it works. Let's move on. But make sure you always investigate. And if there is something funny, think about it. Ask it. This is the kind of attitude that will allow you to grow in this domain. Okay, and then 55. What happens now? So now you see the sidebands, right? So the point being that if I want to see more sidebands, because you know that the resolution of the analysis is not great in the lower frequencies, here I see all of them. So you see, actually, these sidebands are spaced apart by 55 hertz, right? Because you have A plus B, 2A plus B, 3A plus B, and so forth in the negative as well. Okay? So the point being that you get a large amount of spectral components for cheap, so to speak, because I use only 2 oscillators. And you see this would amount to maybe 20, 30 oscillators, just like that. So this is why this technique was extremely popular back in the day when people didn't have many oscillators. It's worth noting that, you know, we live in a hype culture full of crap, if that's an academic statement. And you will hear that John Chowning invented frequency modulation. However, he was the first one to implement it in a digital format. Frequency modulation was used for radio transmission far before that. Okay, so that's typically your sensational, headliney type, you know, phrase. And you know, it's just unfortunate that you can't really count on truth being out there for you, and it's increasingly so, I'm afraid. So your ability to, you know, go to the bottom of things, go and find out is crucial. And the good news is actually that in doing this, you will have to trust your own ability to scrutinize information. Okay, when I was a student, you know, actually it was a bit more boring because everything that I was given was true. So the only task I had was to assume it's true and figure it out and connect it to other facts. But actually, 20 years later already, you know, it's totally different. Cool. So let us first think about this together and then see if we can get somewhere. So what I would like to see now is the sidebands spreading apart. Okay, we've done something similar with AM/RM. How can I do this? What would be the technique to do this? I'm going to show you both of these in the meanwhile, because I'm happy if you can think of it in either domain, in a kind of a graphical or in a code type circumstance. So, first question, let's lead you to it. Okay, that's probably the best thing. So, what determines the distance of the sidebands?
Frequency of multiplier.
Not the multiplier, but the?
Modulator.
Modulator frequency, exactly. Okay, what is the modulator frequency in this patch?
First oscillator.
That's the right answer. The oscillator is not the modulator frequency. Modulator frequency is a fixed number 5. Yeah? So if I want to see them move apart, what do I need to do? Be brave, guys. Come on. I know you know it. Yeah, increase.
Just this number.
Yeah, which is, say the full thing. It's great to practice. Increase the modulation frequency.
Oh, okay.
Yeah. Cool. So, now, how do I increase it? I put in number 10. It still won't show me the spreading, right? I want to see it spread in real time, so to speak. So what can I do in order to achieve this?
Give it a range. Put another oscillator.
The range, well, I think you're thinking about the right thing. You want it to range from small number to large number, but it's not a complete answer, and yours is also from a different side, probably, you know, thinking about the right thing, but it's not an oscillator. Because if I put in an oscillator instead of the number 5, then the modulation frequency will go up and down. But I just want it to rise monotonously. And to do this, I need to use an envelope. And the simplest case of an envelope is what we call a ramp. Yeah, remember the word ramp as well. It's a really neat word. Okay, so which U-gen produces a ramp? You remember from last week, probably? No? No, those were the envelopes. Even before we did the envelope, we actually studied the ramps. I'm afraid you guys really need to spend some time with this in between the classes as well, because it just comes and goes very quickly. And obviously from the last year as well, a lot of things might have went. So I really invite you to invest some of your own time into this. Line, exactly, line.kr. Okay, so what are the parameters of the line? They're typically start, end, and duration, or duration, start, end. Which way around? Sometimes I'm unsure. One way to find out. Start, end, duration. Okay, so I want to start at 0. I want to end at 200, and I want to look at this for 30 seconds. Okay, so this line will produce a ramp to specify the frequency of the modulator. Okay? Is there any issues with this graph? I should say, are there any issues? I've lived in UK for too long to speak correctly. There is one issue, namely, one redundancy. You know the word redundant? Something is superfluous. There's something more than what we need. Well, I've now specified the frequency of the modulator using a ramp, but it's still specified as a fixed number, so there is a contradiction, right? So I, at this stage, invite everyone to remove the fixed value, because now there is no fixed value, it is actually specified by the ramp. Okay, chop chop, your turn. Code it. So this one, I will now also start to take it apart. So I will call, I normally use the tilde variables. The handy thing is that you don't need to declare them. Okay. And actually you can use them across different patches as well, which might be useful. So this is the ramp, and then the modulator will be this one. Okay, oh, and this is actually gonna be my final output, which is actually a sine oscillator running at the modulator signal. And then the ramp was my line.kr, start at 0, go to, what was it, 100, whatever, 40 seconds, something along these lines, except that I need a semicolon here as well. Okay, there is an issue. What's the issue? A bit of debugging brains. Exactly, the 55 is still there, which is my fixed frequency. So instead of 55, I need a ramp. Lovely. Okay, so do I see it? Do I see them spread? That was the idea behind this one, by the way. Let's try again. Cool. All right. Now, the thing about this, these are the, so if we go back to my basic FM sketch, we essentially have three main parameters, which is the modulation frequency, the modulation maximum, and the modulation minimum values. Okay? This oscillator at this stage doesn't do anything, really. Okay? Now, if you have this kind of FM implementation, you can't really connect it to a piano keyboard because I don't have the pitch, right? So actually, in order to adopt this one such that it works more generally, what I need to do is I actually need to maintain a bipolar modulator. What does bipolar mean?
Plus and minus.
Yes. Then I need to multiply it with something that I will call modulation depth. And then I need to add to it something that we call carrier frequency. And then I will get essentially a very similar thing. So you remember now it's probably useful to remember that we've done this with range conversion already, right? So I showed you the, so to speak, manual range conversion, where we multiplied and added with values. Okay. And the reason why in this case it's very useful to have, so to speak, manual range conversion is that now I can actually control the amount of variation, which will be the multiplier, the amount of variation or the amount of modulation or the modulation depth. And I can control separately the center frequency, which we call carrier frequency. Okay, so this means that if my modulation depth is 0, what is the range of the signal here after the multiplier? Right, so I take the output of the sine oscillator and I multiply it with 0, so it's all zeros, right? So this signal will be all zeros, and to that I am adding my carrier frequency, which you could think of as your MIDI key related frequency, which means that if I decrease the modulation depth to 0, I get a sine oscillator based synth, right? Because whatever number comes in for the carrier frequency, it's probably useful if I type these out for you. So this is carrier frequency, okay, and this one, well, actually I should put it here exactly, and this one is my modulation depth. By the way, the depth as a parameter name you probably encountered before, it's all over the place. And typically it will be a multiplier that is the depth, because you understand that if I have a bipolar signal and I multiply it, I'm essentially either growing it or shrinking it or zeroing it out, right? So I'm not really pushing it up or down, I'm just changing the size, which is not the case for unipolar signal, right? Because if I have single 0 to 1, then I'm actually just growing it monotonously in one direction only. And if I have a signal 100 to 500, like I had a second ago, and multiply that, well, then I have to figure out what happens to both extremities in order to figure out what will be the final range, right? So that's why bipolar signals are slightly different beast, so to speak, slightly more robust as well, like that. Okay, so go for it. Let's see it. So please code these variable names, depth and carrier. Okay. Well, for now, I'll specify something. Let this be 500 hertz, and let the modulation depth be factor of 50. So in this case, what we're looking at then is, well, I know it by heart anyway. So we don't have a ramp anymore. We've simplified the patch. We do have a modulator, and we have two parameters. We had the depth parameter at 50, and we had the carrier parameter, at 500. And then you see I don't use simplified range conversion, but instead I do it manually. So I say times depth and plus carrier. And then the final sinus oscillator with the mod. Okay, looks like something's missing. Any clues? What's wrong with this one?
No ramp.
Exactly. Very good. So the ramp is now obsolete. So what do I need here?
Put it as a variable and equal 5.
Yeah, I can put it as a variable. I'll keep it a bit simpler. There we are. Okay. So you see, it's essentially fairly straightforward, I would assume, in terms of the logic. But in terms of, translating, getting quicker with it, you now understand that some of you might need some more practice to be on par with the rest. Cool. So what we're looking at here, essentially, what we've done is we had three initial parameters. What were the three initial parameters? Modulation frequency, modulation minimum, modulation maximum. Okay? And what we've done here is that the modulation frequency has stayed, right? But the minimum and maximum has become depth and carrier frequency. And actually this conversion of parameters is something that you can imagine being useful in multiple cases. So currently, you see, instead of minimum and maximum, essentially what we're doing is we're defining the center and the excursion and the modulation depth. And this will be something you can use in many, many designs. And you can also do it vice versa. You see, for example, if I have to specify a range using two potentiometers or two sliders, two parameters, you see, if I have the minimum and the maximum slider, and I want to keep the size of the range the same, but I want to move it up, what I would need to do is I need to grab both minimum and maximum and increase them in the same way, and hopefully keep the range the same, but it's not likely that it will happen. So, but if I have this type of parameter specification with the center value and the variation around it, then if I keep the variation fixed, I keep the depth fixed, I can just increase the carrier frequency and the whole range will move up and down steadily. Okay? And the same thing holds if I say, well, actually, this is a synth, right? So I need the center frequency to stay at the same value, and I want to change the depth of it, depth of the modulation, then I would again need to grab both minimum and maximum, spread them apart and put them closer together. But with this arrangement, I don't need to do it. I just take the modulation depth and the center frequency stays the same. Okay? Cool. So let us observe this one first. looks like this. Okay, so obviously I don't see any sidebands. So what I'm going to do is I'm going to increase this to 150 and take the carrier up to 2500. And this is a nice display of the sidebands. This is what you actually expect. I'll push them apart a bit further. Okay, so you have the center frequency and you have the sidebands. You see they are equally spaced. Okay, and what you also see is that they are increasingly softer. So actually, theoretically, you have an infinite amount of sidebands produced here, but some of them are just below audible. Now, what happens if I increase the modulation frequency? Exactly, they spread apart. Great. What happens if I decrease the carrier frequency? It all moves down, yeah? And the last one, what happens if I increase the modulation depth? This is the new one, so I shouldn't really be asking a question. But it's good to ask a question because like, oh, I really wonder. And what will happen is if I increase the modulation depth, is that the amplitude of the sidebands increases. Okay? So that's something you want to remember. I mean, just to make sure that it shows as equally spaced, I have to stress that they're equally spaced on a linear axis. Okay? Because the distance is a difference, right? You remember on a logarithmic axis, the exact distance on the axis corresponds to a multiplier. On a linear axis, it corresponds to a difference. Cool. Now, the funny thing to note is that if I increase the carrier frequency here like that, and just try to visually memorize what's going on, and I decrease it like this, it's not really easy to see, but actually the depth, the amplitude of the sidebands actually is affected by the carrier frequency as well. So what we're working towards is actually an even better set of parameters that will keep the amplitude of the sidebands constant, independent of the carrier frequency. And even more importantly, which will keep the harmonicity of the spectrum stable. Because you see what happens now is if I have this sound, this is actually a fairly harmonic sound, right? Now, if I have the modulation frequency set to 274.79, this is an inharmonic spectrum. You hear it, it's much more dissonant. Why? I mean, I can go even further. So I had it 250, I had it somewhere in between. If I set it at 300, again, a slightly more harmonic spectrum. So actually the harmonicity, the consonance of the spectrum is not easy to control. What could it depend on? What makes a spectrum consonant and what makes it dissonant? Well, it has to do with the distance of the sidebands, right? So, you know, the most consonant spectrum is the harmonic series, right? When I have a fundamental frequency and I have integer multiples, right? So what you've seen here when I had it at 250, that meant that the sidebands were spaced apart by 250 hertz. So my carrier was 500, the first higher sideband was 750, second one was 1000, third one was 1250, the lower one was 250. then 0, and then 250 back again, and then 500 back again. So you see, if there is a simple ratio relationship between the carrier frequency and the modulator frequency, then the spacing is related to the fundamental frequency and I get a consonant timbre. Whereas as soon as I do something weird and I do 213.72, we can also check the visuals. I mean, we can't quite see the dissonance there, but we can well hear it, because now if you think about all the sidebands, you will see that they don't have any harmonic relationship. So the problem here that we have is that if I put it to 200, not horribly consonant, but quite consonant. 250 was very consonant. 300, again, was quite consonant, right? If I put 500, totally consonant, totally harmonic spectrum. So you see, as I change the modulation depth, what I get is certain peaks of consonance and then valleys of dissonance in between. On top of that, if I call this a dissonant modulation frequency 330, well, that wouldn't be one. Let's do 321. Okay, fairly dissonant. But now I change the keyboard pitch, and instead of 500, I get 621. Or even worse, if I accidentally get 642, then I suddenly get a consonant spectrum timbre, right? So actually, you see, the issue here is that if I want to make a decent FM synth, I would really want to stabilize the harmonicity, as we call it, of the spectrum. Which means that I really need to come up with a different way of specifying the parameters. So actually, I'm not looking at adding another oscillator, adding a filter. I'm still down to two oscillators, like I was in the first instance. In the second instance, we've made it slightly more intuitive, but it's still problematic. Okay? So the solution to this, and I will show you the one in, well, this is a project I'm working on. I will show you one in Max MSP in a second. Oh, why is that? Doesn't want to work. Is this to 11? Huh, that broke. Crazy. Max for Live? No? Okay, I'll just run it briefly from here. Max 2, max, whatever. Because actually what we want then is the harmonicity parameter. Any ideas how we can get to the harmonicity parameter? It's not an easy thing to come up with. Like with this, hopefully this will start in a second. Looks like my thing is broken. It worked most recently. Uh-oh. Where is this thing happening now? Max 8. Aha. Here we go. Okay, so in Max MSP there is a little patch called Simple FM, and this is the one that shows you how it's done. Okay, so you see it's actually fairly similar to what I've been drawing. So this is my modulator, this is my carrier. Between the two I have an amplitude or modulation depth, and here I had carrier frequency. Okay, now this is the thing that we can do. So if we make it such that the modulation frequency is the multiple between the carrier frequency and the new harmonicity parameter, what does that mean? It means that the multiplier, the the relationship between the carrier frequency and the modulation frequency will be a fixed value, right? So this means that if this value is, let's say, 0.5, if I have 440 hertz pitch, my modulation frequency will be 220. So it will be a very harmonic spectrum. If I move the carrier frequency to 621, you see the modulation frequency will move along and it will be 310.5. And I will retain the harmonicity of the spectrum. You see, so this is the trick. To create the harmonicity parameter, you actually make sure that the modulation frequency depends on the carrier frequency. It's still not going to be a linear parameter such that, you know, you increase the harmonicity as you increase the parameter, right? So it will still be your valleys and peaks, right? So if I have an integer number there, or the reciprocal of an integer number like 0.25, 0.1, all of these things, I will get a fairly harmonic spectrum, and most importantly, it will stay harmonic across the range of carrier frequencies, across the range of pitches. Make sense? Similarly, in order to stabilize the amplitude of the sidebands, what I'm doing here is I'm taking my modulation frequency, which is now the product of harmonicity and the carrier frequency. I'm taking this to be, times modulation index, which will be my actual sideband amplitude parameter. It's a bit harder to explain why exactly, but the point is that if my carrier frequency increases and my harmonicity ratio increases, right, then the amplitude of the sidebands will change. So essentially, I am compensating for that. Okay? So this now is the more robust set of parameters for the same thing. We are still down to 2 oscillators in a frequency modulation configuration. Okay? Cool. So this is the task for the break, and join it with the break. So we'll take a generous 25 minutes break. 20 is enough? Let's take 20 to 25 minutes break, okay? So we'll start at 7 back again. So you can choose which way around you want it. First the exercise or the break. And then we'll take. Okay, guys, so let's look at the solution together. So here is my code from the previous attempt. And the difference here will be that the depth will be not a fixed number. It will be derived from the other parameters. And the new parameters here are harmonicity. And I will pick a 0.2 to start with. Oops. Best if I look at my screen instead. Okay, carrier frequency remains a parameter. And the other new parameter here will be index of modulation, modulation index 33. Okay, so this is the new set of parameters that we will try to use. Now, the modulation frequency is now the carrier times the harmonicity. You see, it connects the two, meaning that if I have a simple ratio or an integer or a reciprocal of an integer there, then I will retain a harmonic spectrum, and otherwise I will have a fairly inharmonic spectrum. And then the depth, funnily enough, is actually derived from modulation frequency, which is then multiplied by the index of modulation. Yeah? And then actually this one stays the same, except that this is now my mod frequency. Okay? Modulation signal is modulation frequency times the depth plus carrier, and this is the final thing there. I have one too many tildes here. That's what it is. Okay, so this one corresponds to this thing. Cool? All right, so let's have a little play with this now. I would like to demonstrate that now I can play music with this synth, and thanks to this arrangement of parameters, the timbre will stay the same. That was the point of this, because in the previous configuration of parameters, things were all over the place, which is cool if you're making noise music, but if you want to do something melodic, you really need this set of parameters. Okay, so let's roll back a bit and try to create a set of pitches that I will choose from. So I'm now working a bit towards my least favorite musical element, which is arpeggio. And I would like to divide the octave in 6 equal steps. You remember? Well, now you will. Okay, so how did I do this? What was the math? Can anyone explain this to me? I have an octave. Let's say my fundamental is 360 hertz. Whatever. What is the octave on top?
720.
720, exactly. What is the frequency halfway? And it's not equal difference, it has to be equal multiplier. So it will not be 180 plus 360, which is 540. Will it be higher or lower than that?
So what was the question?
So I'm looking for halfway the octave. I'm trying to split the octave into 2 equal parts, and I cannot do it by having a fixed difference. So if I was to do this to split the table in half, which is a linear thing, then I take the difference, divide by 2, and add that to the bottom, right? So if the table was starting at 360, ending at 720, right, it would be 540 halfway. But because I'm in the frequency domain, I'm on the logarithmic exponential scale, what do I have to do? This is something we've studied a few weeks back. Instead of having a fixed difference, what is fixed?
Multiplier.
A multiplier, perfect. Okay, so I know that my multiplier, let's call it x. If I multiply 360 with x, I will get the halfway frequency, and then multiply by x again, I will get the octave. Which means that I'm multiplying twice with x, which is x squared. And x squared equals the octave, which is 2. Therefore, x is basic math. If x squared is 2, then x is
1.4.
approximately, which is, why is it 1.4? It is the square root of 2. Yeah? Because x times x has to be 2. X is square root of 2. Okay? So I can just verify that. If I take 2 to the power of 0.5, that's 1.41. Okay, so remember that we take the root by exponentiating to the reciprocal of the root. So if I take the second root, it's to the power of 1 over 2. If I take the third root, it will be to the power of 1 over 3. Cool? Cool. Now, I've divided it in two, so let's just make sure I did. So the way I can look at these values, if I take an array, a geometrical array, that starts, has a size of 3, so I see all 3 frequencies, start at 360, and the growth is 2 to the power of 0.5. And there it is. I have 360, 509, and 720. Okay, so I verified that this math works. I've actually split it into 2 equal ratios. Cool. Now I want to split it in 6. What do I do? So you see, it's a similar story. I start with 360, and I have a new x, the new unknown ratio. If I do 360 times x, times x, times x, times x, times x, and times x, I will get the number 2. I will get the octave. So the x is the 6th root of 2. Cool? All right, let's see it happen. So that will be here 2 to the power 1 over 6. And now I want 7 values just to verify that the octave is there as well. And if everything goes right, I start at 360, I end at 720, and these are my frequencies. Make sense? So I have managed to divide it into 6, and this will be my scale. Cool? Cool. Okay, so in that case, I don't need the fundamental here. So what I need to do now, what I can do many things, but essentially the simplest way of making something melody-like out of this would be to get a stepwise function that runs across these frequencies specified in the list. Okay, it's not something probably not something you have studied before. I have T-rand, am I saying this right? T-rand? D-rand, huh? T-rand? So put my memory. P-rand, yeah, that's for patterns. Let's see if I can find it. So there is a class of triggered eugens, which are convergent Bella generators analysis, algebraic. Let me make sure that I'm doing the right thing. Synth control, I think it has to be in the generators. Single value generators, DC, silent, stochastic, physical, deterministic. Uh-oh, it's not there. Demand rate. Okay. So here, dsec, nope. Well, there's a T duty. Demand results as a trigger. Interesting. Let's see. Random. Okay, so here I have it. Single random number generator. Rand. Okay, and this one will have a low and a high. And it is... it looks like things have changed. Because there used to be a T-rand, and now it's slightly different. Well, that's a good thing. We can study this. The issue is that I don't see a way of triggering it.
We do have a T-rand.
Do you?
Yes, just ladder T and ladder R.
Well, that's what I thought. Ah, there we go. So things didn't change that badly. Okay, so we have this. So I could choose a random value between low and high for every trigger. However, I don't want a random frequency. I want to pick from this array. And for that, there used to be, and hopefully still exists, is the T-choose. No. Let's see, what are the T things? Linrand, object triggered triggers. Okay, so T-choose, there it is. Why didn't it find it? Oh, there we go. So the T-choose is the one that will randomly select from an array, from a list, based on a trigger. Okay, so what I'm gonna have here then is that my carrier is a t choose. Okay, well, I can do AR, I don't really care. The trigger is, you've seen impulse being used as a trigger, and I've explained how you can use actually any signal, but we'll keep it simple. We're gonna take one new value every second, and my list will be the scale. Okay, so if the scale is there, the scale is there. That should do something, except what's happening here? The error message says last index not understood. Arguments protected call stack. Which object doesn't understand? Carrier. T choose.
A semicolon on the scale.
On where?
On the scale. When you
Yeah, I didn't execute that together, so that was already there. So that shouldn't be an issue. So last index, for some reason, is the scale. Did I spell it right? Scale. I mean, it should be in the context, but let's bring it in anyway. Maybe it's lost, but it shouldn't be. Try it like that. Because the last index is typically the thing that it calls to get the size of the array. Scale is array geometrical. What's up with this? Let's see how tree choose is used. Dust AR mouse KR A. Dust AR mouse AR K. And the A is, yes, it's true. It is a list of oscillators. Okay, so there is such thing as getting an oscillator from a fixed value. Let me just remember. I think it's I can probably do K to A dot AR and then the in. Okay, so for each of the values here, I will actually get a Eugen. Would that work? Still doesn't work. Last index K to A. There was a way of doing this. Let me just think. You see, it's complaining because I'm not having generators in a list, but I'm having fixed values. Let's see if I can find it. It rings a bell in terms of how this is done. In, out, generator, stochastic. It could be in here, blip, no. Shall we see if ChatGPT knows SuperCollider? Let's see. Huh?
He does a bit.
He does a bit, yeah? Let's see. How do I make a fixed value Eugen in SuperCollider? Haha. Let's see. Fixed DCAR. There we go. Clever. Okay, so let's try that. DCAR. Still. Oh no. 7. Oh, yes, exactly. It's me being stupid. So this is the actual start. And this is the number of things. Yeah, I would need a function for that. Okay, so what I'll do then is I'll keep this the scale. I'll call this the frex. And then the scale will be array.func, I imagine. Does that not work? Array.fill. Yep. And then we have the size, which is frex.size. And the function is taking the frequency, give me a dc.ar at that frequency. Okay, did I hack this well? No, come on. Come on, it's still the same one, no? Let's see if I pull this, what happens. Without the choose. Well, let's just comment out everything here. Okay. No, the other way around. Zero, 1, 2, 3, 4, 5, 6. Eugen array at the element. So let's print this f post ln. So you get a bit of debugging practice here. Yeah, well, that's wrong. I don't want frex to be that. That's weird. Post ln. So this is the array of frequencies. Array.fill frex. Oh yeah, I have to index into the, yes. So because this is the index, so what I need to do is frex at f. And that should do it. Okay, yep. So I have this array, and then that should do it. Fingers crossed. Oh, what the hell is going on? Let's see it. So what I'm saying is that I'm taking the dcar fill frex size. So what is this scale thing? The scale now has to be full of Eugens, dcar Eugens that have the fixed value. Again, I need to comment this out. Okay. An output proxy. Ooh, that's strange. Now if I do a kr, probably doesn't do much with this. Still the same. Output proxy. Array fill frequency that size gets this, takes that. What if I put just the f? I mean, I'm a bit puzzled why this. I probably did a. Okay. So that. Oh yeah, because it's commented out. That won't do. Let's see. Still the same error. Still the same error. Uh-oh. Uh-oh. So the scale is invariably... It didn't even print the scale at this stage. Last index. T choose from the scale. Well, I'm a bit puzzled, I have to be honest, at this stage, because this should just plain work. Let's see the DC help file. I'm not sure why it actually, also it cannot be modulated, setting it, yeah. DC. Oh, well, that's me being totally stupid, right? Because that's the one to put in there. That's the value. Okay, now, DCR frex at f. Let's see. Yeah, well, I have these output proxies. They don't seem to do the thing. Yeah, and those are the values. So there's something rather strange. It might be a buggy thing, to be honest. because I'm actually giving it the range of hugens that are doing it. Okay, well, bust that. Instead, oh no. Let's do the random frequencies. Who cares? I've messed this up a bit as well. Let's clear that. So instead of, well, at least there is a technique there. I mean, with the P, I don't want to go into the patterns. I see you have studied it, I imagine, with András. But I was keen to show you how it would work on the server. But anyway, so now what I'm going to do instead is I'm going to say that the carrier is an LF noise 0, oops, dot kr, which is my stepwise function at the frequency 1, and I will have the range of 300 to 600. Okay, and then semicolon. Okay, so what I'm trying to verify is that now the timbre is fairly constant. You kind of believe that it is a single synth, right? If I change the harmonicity, let's try 0.67. See, again, I have a fairly constant timbre. So actually the harmonicity parameter becomes the timbre parameter. Let's try 1.67. Fairly believable. And then the index will actually be the amplitude of the sidebands. Okay, so if I take this down, I will have the same timbre but less articulate. Yeah? And again, it does sound like it's the same instrument. Okay, so to wrap it up, what I will ask you to do is produce another good cue, perceptual cue, for producing a single instrument sound. So one of the things that makes this sound, let's say, coherent is that the spacing of the sidebands is related to the carrier frequency. Okay, in other words, the modulation frequency is related to the carrier frequency. And the fact that the level of the sidebands is also fixed across different carrier frequencies. Now, typically when you have an acoustical sound source, an instrument, one of the main cues why this appears to be a single sound source is that there is a fixed filter characteristic. Okay, so actually what I'm doing here is I'm changing the characteristic of the underlying excitation signal. And in order to produce an even more believable instrument, I need to produce a fixed resonance. Okay, so if you look at the guitar, I think I saw a guitar here, there it is. What you have is that the excitation is the string and the resonance is the body of the instrument. So because of the body of the instrument is such, it's a fixed acoustical body, it means that the resonance frequencies will stay fixed independent of the underlying excitation. Okay? So this is what we can try to achieve. So what I will ask you to do then is to this patch, and now I'll just produce a textual instruction, add 4 resonant bandpass filters in series or in parallel. Or both. So I'll ask you to think it through. You do understand what does it mean to connect things in series and to connect them in parallel? Let me just make sure that that is clear. So when you connect things in series, what you get is let's have multiple processes. Okay, if I have let's do 4 to start with. So I have 4 things, A, B, C, D. Okay, connecting them in series means that A goes to B, B goes to, B goes to C, and C goes to D. I will omit the arrows now to save some time. And then to connect them in parallel, can anyone tell me what does it mean? It actually means that they have a common input and they have a common output, and the way they connect, line label, no. The way they connect will be such that every process shares the input I think you get the idea, but let me just draw it. Oh, come on. Come on. Let me just draw it through. So, okay, now it stays. I still can learn this program. And all of them go to the output. Okay? So that's the main thing. This is a connection. To the left is the connection in series. This is connection in parallel. And the one thing that's missing is that typically you have to sum these things. So actually there is a plus there. And then you get your output out of there. Okay? So you want to think it through already? What makes sense in terms of connecting 4 bandpass filters? In series or in parallel? Why? I mean, it's a good guess. You know, I would bet on it. But I would prefer to hear why. What would happen if I connect bandpass filters in series? What would happen if I connect them in parallel? So, first of all, let's realize what does a bandpass filter do. If I have white noise, which is flat spectrum, and I put a bandpass filter on, what I get is narrowing. And potentially quite radical narrowing, which means I'm excluding all the other frequencies. So if I take this, let's say this is 200 Hertz bandpass, and I put it in series with a 1 kilohertz bandpass, it has a peak elsewhere, right? So if I put them in series, it means that after the first filter, I have already removed the 1 kilohertz energy, right? So once it comes to the second filter will remove the 200 hertz energy. And then the third filter will remove both of those and won't have anything to keep because that frequency was already removed. And I shouldn't say frequency, I should say bandwidth. Okay? Because it's about the bandwidth. It's not one single frequency being removed. Okay? So that's the argument. If I put them in series, these filters will cancel each other out. Right? If I put them in parallel, this means that the flat spectrum will have a 200 hertz peak, but I will add to it the other peaks. Make sense? Okay, so I will make this clear that add 4 resonant bandpass filters in parallel. Okay, this is your task. So you can, well, you pretty much have the code already. Maybe add the noise signal. Okay. And then let's see you connect 4 bandpass filters in parallel. If you feel that this is really challenging, it's supposed to be, but I'm happy for you to just draw it. Okay, if you think, well, I cannot code it right now, but it's important to first understand what it means, and I already had a little drawing how things look in parallel. So I would like you to draw it. If you can code it immediately, code it. In any case, I will not give you the solution now, but I will ask you to work on it tomorrow morning. Okay? We have another 15 minutes of the class, so I will help you out. I will not give you the solution, but just steer you or us answer the questions. And then tomorrow, first thing, we will look at full solution, both the graph and the code. Make sense? Cool. Get going. So this is the end then for the recording. Goodbye.